Hello, this lesson video is going to be all about evaluating functions. And tied to this lesson is the learning target that I can evaluate functions in different forms, like if the function is a graph, including piecewise, if the function is a table or ordered pair or rule, etc. So what does it actually mean to evaluate a function? Well, to evaluate means to bring a value out of the function, right? So what are the two values that we could possibly be talking about with a function is either finding the function's output, if you're given the input value, or finding the function's input if you're given its corresponding output. So we're going to take a look at how to find those two things, inputs and outputs, of a function in different forms today. We're going to start with evaluating a function that's written with function notation, okay? And that's basically like when we say a function rule, that's what we're talking about in this case. And this is where we use our function notation. And I just want to remind you what function notation looks like. All right. So where we have the thing in parentheses is the input value. And remember the letter in front here, in this case it's f, but it could be any letter. This is the name of the function. So this function's name is f, and x is the input of the function, and what it's equal to is the output of the function. In this case, it's y. So when you see f of x, that's equivalent to just saying y. All right, so x goes into the function, some kind of function is being performed on that x or that input, and out of the function comes y, or the output. So what do we do? How do we evaluate if we know the input and need to find the output? Well, remember that we're performing some function on the input value. So all we need to do is simply substitute the input value that we know into the function and get the output. Here's an example, okay? So I'm right here. If f of x equals 2x minus 1, I'm going to stop right there because let's just take a second and think about what's going on here, okay? So I'm saying this is function f, and x is the input, right? So what's happening to the input value? What is the function rule? Well, the function rule says that first thing we're going to do is we're going to multiply the input value by -2, and then we're going to subtract -1, right? So we're going to multiply the input value by -2, and then we're going to subtract 1 from that input value. So what is f of -3? Well, remember, a -3 in this case, this is saying that the input value is equal to -3. So f of 3 would look something like this. Instead of -2 times x, now x is equivalent to -3. Now the input is -3. And so f of -3 is equal to -2 times -3 minus 1, which is 6 minus 1, or 5. So f of -3 is equal to 5. We can write it like this, or we can write it as a set of ordered pairs. It would look -3, 5. That's another way to do it. Of course, you could write this in the table or write it as a mapping. But this, when it's in function notation, is perfectly acceptable to leave your answer like this. Of course, this example was a numerical input. We can make anything the input or the domain into a function. We could use numbers, variables. We can even have expressions, whole expressions as inputs. And what I want to do is take a minute and look at what happens if that's the case. So again, it's the same function f, right? F of x equals -2x minus 1. Then what is f of a? All right, well, instead of x being the input, a is now the input. So anywhere we see an x, we are going to replace it with an a. So instead of -2x, it's going to be -2a minus 1. And because we can't combine anything together there, this is really as far as we can go. f of a is equal to negative 2a minus 1. What about if the input is an expression like x plus 1? Well, again, anywhere that we have an x or our original input, we are going to replace it with x plus 1. Okay, so it's going to look like f of x plus 1 is equal to negative 2. Now, because the input is an expression, I want to make sure that the whole expression gets kept together. That's why I'm going to put it in parentheses like that. In fact, it's actually a pretty good technique or a good strategy that anytime you're substituting anything into an expression that you make that substitution with a set of parentheses. And we could simplify this a little bit more if we distribute. Okay, so negative 2. So again, we're going to distribute, and we get negative 2x minus 2 minus 1. And then we do have some like terms we could combine together. So f of x plus 1 is going to be equal to negative 2x minus 3. So when we input x plus 1 into function f, the output is negative 2x minus 3. These three examples were examples of when we're given the input and we need to find the output, but we could work backwards too. What if we know the output and we need to find the input? So if we know the input, if we know the output, all we need to do is set the function equal to that output and then solve it for the input variable. For example, if f of x is equal to 2x plus 9, what value of x makes f of x equal to 7? So if f of x is both 2x plus 9 and f of x is equal to 7, that means that 2x plus 9 is also equal to 7, right? So we take our function and we set it equal to 7. And from here we can actually solve. So 2x is equal to negative 2, and that means x is equal to negative 1. Now what does that tell us? That tells us that if we do f of negative 1, in other words, if we make negative 1 the input into my function, I should get 7 as my output. So let's just think about that. 2 times negative 1 is negative 2. Negative 2 plus 9 is 7. There it is. So we can evaluate a function in function notation given an input or given an output. Oh, here's another one. If v of t is equal to negative 1/2 t plus 2, what value of t makes v of t equal to 2/3? So again, the 2/3, the number we're given, is an output, right? If it were an input, it would have been found in parentheses. It would have been in here, right? It would have been here. But it's an output. So we're not substituting 2/3 in for t. Instead, what we're doing is we're taking our whole function and we are setting it equal to 2/3. So negative 1/2 t plus 2 equals 2/3. A little solving for t. All right, we're going to do 2/3 minus 2. 2/3 minus 2. Well, 2 is 6/3. So 2/3 minus 6/3 is negative 4/3. So negative 1/2 t is equal to negative 4/3. And then we need to multiply both sides by negative 2/1. Negative 2/1. And that'll eliminate these guys, and we get t is equal to, remember we multiply across and multiply across, we get positive 8/3. So t is equal to 8/3. And that tells us that when the input is 8/3, the output is 2/3. Let's look at one more interesting example of a variation of this same kind of idea. If f of x is equal to 3/4 and g of x is equal to 1/1 x plus 1, what value of x makes f of x equal to g of x? All right, well, it tells us that f of x has to be equal to g of x. So if f of x is 3/4 and g of x is 1/x plus 1, then and it tells us that they have to be equal to each other, then we have an equation that we can solve for x. And this my friends, is a proportion. And perhaps you remember that when we solve proportions, we cross multiply and we set the cross products equal to one another. So let's start with 3 times x plus 1. So we have 3 times the expression x plus 1 equals, and then we'll do the other cross product, which is 4 times 1. Distributing here, we get 3x plus 3. And on the other side, 4 times 1 is 4. Little solving, 3x equals 1, which means x is equal to 1/3. And what that means is when the input into function f and function g is 1/3, then the outputs are going to be exactly the same. So remember that functions can come in many different forms, not just function notation. They can come in the set of ordered pairs or a table or a graph. So we're going to continue looking at this in different forms. All right, so we're going to consider the function g of t is equal to that set of ordered pairs. And maybe you remember that each ordered pair is an input and an output, right? It's an x and a y in some cases, or in this case, if you look at our function, it's not x and y, right? Look at our function here. Our input, or our domain, remember our domain and input are the same, is t. So this first number in each one of these is a t value. T, 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 t. And the output is going to be g of t. G of t is the output. G of t, and so on. Okay? So here's the question. What is g of 0? So if t, that thing in parentheses, remember that's my input, that's the first number in each pair, is 0, what is the output? So right here it is. Look at 0, 3. So g of 0 is equal to 3. When 0 goes in, 3 comes out. What domain value has a range value of 8? Okay, well, remember domain is the first number, range is the second number. So we look for the pair that has 8 as the second number, and it turns out that the input value or the domain value is 5. What value of t makes g of t equal to 1? All right, is that 1 an input or an output? It's an output, okay? So we're looking for an input value that makes an output value of 1. That would be this guy right here. So the input value of -2 gives an output value of 1. So t is equal to -2. The same kind of rule applies when we're talking about a table of values, right? So remember that the left-hand column is the domain or input, and the right column is the range or the output. What is c of 7? Well, when the input is 7, the output is 43.96. What value of r makes c of r equal to 12.56? Well, this time, what input value gives you an output value of 12.56? Well, that's when r is equal to 2. Very straightforward stuff. It's kind of like matching up pairs, right? We can also get it from a mapping, right? Let's consider this. This mapping is of function f, and a is the input value. So a is the first set of values, and then f of a, or the output, is going to be the second set. So what's f of 5? Well, when the input is 5, the output is 0. What value of a makes f of a equal to 2? Well, this time we're kind of working backwards, right? The output is 2, the input is 4, so a is equal to 4. Straightforward stuff. How about we look at some graphs? It's important to remember that a graph is nothing more than a visual representation of all the pairs, just like a set of ordered pairs or a table. So each point on the coordinate plane represents a pair. Let's look at this discrete graph Each one of these points is a pair of function f, okay? So what is f of 2? Now, 2 is an x value. It's an input value. So we go to 2 on the x axis, right? Remember, that's the horizontal axis. We go over to 2. There it is. And then what we do is from 2, we go up or down to try to find the point. And there it is. So when x is 2, what is the y value for that point? The y value is 1. So that's the y value. The output is equal to 1. The second question, what value of x makes f of x equal to 0? All right, that 0 is a y value. So what I'm going to do is I'm going to start on my y-axis, and I'm going to go to 0, and that's right there at the origin. And then I'm going to go left and right and try to find a point that's right, that has a y value of 0, and there it is, right? What is the x value or the input value at that point? Well, it's 5, so x is equal to 5. So when you have an input, that's your x, you're trying to find the y. And when you're given an output, that's the y, you're trying to find the x. Let's take a look at, this time, a continuous graph. The graph below is of the function t of x, where x is the number of hours since midnight, and t is the temperature. In this context, what does t of 12 mean? All right, well, tell me what the 12 means. That's where the x goes, right? And x is the number of hours since midnight. So that tells us that we are 12 hours from midnight. What's 12 hours from midnight? Oh, it's noon. So this t of 12 means the temperature at noon. The temperature at noon. And what is the temperature at noon? Well, it's 12 hours. Here's 12 as my input. I'm going to go up, 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 up. There's where it hits the graph. And then I'm going to go over to find the output. And it turns out that at noon, the temperature was 110 degrees. Holy smokes, that's really hot. In this context, what does t of x equals 105 mean? All right, well, remember, x is the hours since midnight.
Ryan Glazer to the main office.
105,
Ryan Glazer to the main office.
This would be the temperature. So at what time, or more specifically, how many hours after midnight? How many hours after midnight? The temperature was 105 degrees. Okay, that's what t of x equals 105 means. How many hours after midnight, I forgot that word, midnight, the temperature was 105 degrees. So this time, I'm going to change my color here so we can see. Let's see, where's 105? Right about in the middle here, right? 105, this is the temperature now. So now I'm going to go over. Oh, I'm going to go all the way over, and I noticed something. I noticed that it actually hits the graph here and here, 2 places. So there are actually 2 times where the temperature was 105 degrees. The first one, it looks kind of like 10 hours after midnight, right? So that's 10 a.m. And then it happens again, like, let's say, 19 hours after midnight? What's 19 hours after midnight? 19 hours after midnight would be 9 p.m. So it hit 105 degrees at 10 a.m. and 9 p.m. Craziness. The last thing we want to do is look at something called a piecewise function. I think I'm going to make this a separate video. You've been watching this long enough. Take a look at the next video on how